Welcome back to eCoreAcademy, everybody. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. Today, we have an Algebra 2 lesson, and we're going to be continuing off of dividing polynomials. This video is going to focus more on a theorem. Theorem, remember, is just something that we scientists and mathematicians have developed that has shown some precision because it can be replicated, but it's not like a law. It's not set in stone. But this rational root theorem that you see up here, it's really useful when it comes to finding the solution specifically of polynomials. So before we even divide, to figure out how many solutions is a polynomial going to have, the rational root theorem is going to help us with that. I next want to show you what we're going to be learning about in this video. So again, we're first going to be learning about this first theorem. It's about rational roots. As you can see, rational root theorem is going to help us in reducing the number of roots of polynomials. So what does this mean? The rational root theorem, we'll think of the word rational. When we talk about rational numbers, we're talking about numbers we can express or have a finite number of digits when expressed as a decimal, or have a set series of digits that repeat as a decimal. However, the opposite, an irrational number, has a slew of infinite digits that are random, that do not have like a set pattern of repetition. In addition, if you throw in things like imaginary numbers and things like that, that's an irrational number. So the rational root theorem is mainly focusing on, well, if we look at the next word, roots are x-intercepts and also known as solutions. They are the solutions to a polynomial. So when we factor a polynomial, they're where the polynomial intercepts are touches the x-axis. This means that the roots that the rational root theorem is going to help us find are going to be all the rational roots of the polynomial that we're looking at. We can also use these rational roots to help us find irrational roots. So we are accounting for rational and irrational, so all roots of the polynomial. It just depends on what the problem is asking, and you'll see exactly what I mean. So before I dive into the video, I want to show you this meme we have up here. It says fourth degree polynomial. So this is x to the fourth power as the leading term, maybe some coefficient in front of it. You're panicking because we really only know how to factor quadratics in the most comfortable way. Then you realize I can use the factor theorem, the rational root theorem, and you're more calm. Then you realize that there are 20 different numbers using this p of x equals 0, p of x is the polynomial. When you set the polynomial equal to 0, you realize there's so many roots that belong to this polynomial, and you begin to panic again. I'm going to show you some tricks to find all the rational roots, the possible rational roots of a polynomial, and then narrow it down to which ones are actually roots of the polynomial. And that's what we're going to cover today. So please like, subscribe, hit the post notification bell, drop a comment down below, and share using all of our socials. And let's jump right into the video. So first, let's cover a key concept so we understand what exactly are we learning about. The key ideas that I want you to take away from this lesson and the next one that's going to follow, that's going to be on the conjugate root theorem. About this lesson, we want to be able to solve equations using the rational root theorem, equations in the forms of functions p of x. We want to be able to make that an equation, factor it, and then find the roots or solutions of the polynomial using this rational root theorem that we're going to learn about on the next slide. In the next lesson, we'll talk more about what the conjugate root theorem is and how we can use that to also solve for a polynomial's roots, x-intercepts, or solutions, whatever you want to call them. Let's talk about what the rational root theorem is simplified. It is used to minimize the possible number of roots of a polynomial. So what does that mean? If we have a really large polynomial or the leading term is to a very high degree, like past a cubic degree, then it becomes really tough for us to factor and figure out what are all the roots or solutions to that polynomial. The rational root theorem that I'm going to show you is going to help us narrow it down to what are all the possible solutions to a polynomial, and then going through those possible solutions, we can figure out which ones are actually roots of the polynomial. So the rational root theorem is supposed to save us time when we cannot factor by guess and check method a really large polynomial. And I just wanted to throw this in there as well. So if you're like in depending on whatever Algebra 2 class you're taking, because often high schools, especially in the United States, will offer different levels of Algebra 2. If you're taking more of a college prep or accelerated class, meaning you're taking a bit of a lower level Algebra 2 class because maybe math's not your strong suit, and that's perfectly fine. You are going to be allowed to use a calculator to find the first zeros. Remember, on your TI calculator, you're graphing on the rational number plane or the real number plane, so you can find rational zeros on there, and then you can use those to help you find any other irrational zeros, including maybe repeating decimals or imaginary numbers, etc. So you're allowed to find that first rational root using your calculator. However, if you're in an honors or an advanced level class, whatever your school might call it, you're probably not going to be allowed to use a calculator. You're going to have to figure everything out by hand, because in this case, a calculator helps you quickly graph. So what you would end up doing is graphing the polynomial, then graphing the line y equals 0, which is the x-axis, and then finding the intercepts, which you should be able to do, finding the intercepts of a line. And you would find the intercepts to find the first zero or zeros, and then you would use those zeros and use the rational root theorem, or the second part of the rational root theorem, which I'm going to show you, which involves synthetic division, to find any irrational zeros, because you obviously can't find irrational zeros, including things like imaginary numbers, on your TI calculator. However, in advanced or honors classes, you're not going to be allowed to use a calculator. You got to do everything by hand. More time, more work, but you have to be able to do the same amount maybe a person taking a lower level class is able to do in the same amount of time, if that makes sense. So just be prepared for that. Here's the rational root theorem. I bet you're dying to know what it's about. So the rational root theorem, in this case, we're going to let p of x, which is going to be some polynomial, equal a subscript n times x to the power n plus a subscript n minus 1 times x to the power of n minus 1 plus ... whatever terms come between them, all the way to a subscript 1x plus a subscript 0. What does this mean? Well, this means it just represents a polynomial. This first term here is going to be our leading term. A is the leading coefficient. X is the x value that goes with it, and n is the degree. So let's say we're talking about a cubic polynomial. Well, this would be x cubed with some coefficient a. And then what this represents is that we are actually reducing the degree of each term. So if this was a cubic, then we go to a quadratic next, which, because it's 2, 3, 2, then we keep going until we got to a linear term, because you see this x doesn't have a exponent, so we pretend it's 1, and then you go all the way to the constant, which has an x term of x to the power 0, which is 1, so 1 times whatever the coefficient, or in this case constant, is just going to be equal to the constant. So this is just showing us a polynomial with terms arranged in descending order. It's separated by an addition in this case, or it could be a subtraction sign. So this is going to be a polynomial with integer coefficients. So a is the coefficient. These are all going to be integers, positive or negative real numbers. Now we're being told there are a limited number of possible roots of p of x equals 0. Remember, when we want to find the roots or the solutions to any kind of polynomial or function, what we do is we set it equal to 0. Remember when we talked about quadratic functions, what we did was we factored it, but if we wanted to find the actual solutions or x-intercepts of the quadratic, we'd set it equal to 0, and then we'd work from there. So we're trying to find the amount of roots p of x has, and we're going to do that by setting it equal to 0, and we know that even if the polynomial is really long, it's not going to have an infinite amount of roots or zeros or solutions. It's going to have a limited number, but this limited number is going to be a lot more than we're usually used to finding, which is maybe 2 from the quadratics. These integer roots must be factors of a subscript 0, and the rational roots must have reduced form p over q, where p is an integer factor of a subscript 0, and q is an integer factor of a subscript n. So what does this mean? Well, think about it in terms of quadratics. We had ax squared plus bx plus c. We wanted to use the guess and check method. We'd find out what the factors were of c, which is the constant, and we would use those to figure out how we would set up our parentheses x plus or minus some value. So this is what this means. Integer roots must be factors of a of 0, which is the constant, so we're trying to find the integer constants of a of 0. We're also trying to find the rational roots, and they have to have reduced form p of q. So p represents an integer factor of a over 0. So a over 0, we're going to figure out what the factors of a over 0 are. Then q is an integer factor of a of n. So we're trying to find the coefficient of the leading term and then find the factors of this coefficient. We're going to find the factors of both the leading term's coefficient and then the constant. What we're going to do is we're going to set up fractions. We're going to put each of the factors of the constant over each of the factors of the leading coefficient. And what's this going to do is going to create a bunch of fractions, or maybe not fractions, depending on what the values are. We're going to have a bunch of numbers, and then these are actually going to be the possible solutions of the polynomial. Then we're going to use these to figure out what the actual solutions are. So here you have an example. You have 21x squared plus 29x plus 10. In this case, this is a subscript n, so you're going to find the factors of this leading coefficient. They are, well, if you just look at 21, you know the factors are 1 and 21, 3 and 7, and make sure you add a plus or minus sign. This is very important because these could be positive or negative. We're talking about all integers. Integers are positive and negative numbers. Then we're going to look at a subscript 0, or the constant, which is 10. Factors of this term are positive or negative 1, positive or negative 2, positive or negative 5, and positive or negative 10. Then what we can do in this case is divide everything by 21 so that the coefficient of the leading term becomes 1. So we get this x squared by itself, and if we do that, we get x squared plus 29 over 21x plus 10 over 21 equals 0. Then if you use some other methods that I'm going to show you, you'll figure out that the roots are negative 2/3 and negative 5/7. And you can actually see that what we did was we took one of the numbers over here and we made it the numerator, and took one of the numbers over here, make it the denominator, and we found the two actual roots of this quadratic. And because they're not integer values, because they're not whole number values, it's not easy for us to use the guess and check method. That's why we use this method, and we get x plus 2/3 times x plus 5/7 equals 0. So that's how you would solve. So let's go through a few problems. Here's problem number 1. What are all the possible rational roots of 2x cubed minus x squared plus 2x plus 5 equals 0? Then we're going to find all the roots, all the actual roots. So we're going to find the possible roots, then we're going to find all the actual roots. This is a cubic, so it's not going to be easy for us to factor, so we can actually use the rational root theorem. In order to do this, we're going to locate one root, and once we hit on that one root, we're going to use synthetic division to break down the polynomial we've been given until it's a quadratic, and then factor from there. So here's the solution. I'll walk you through it. So we're going to take the original polynomial we had. I don't exactly remember it, sorry. And we're going to focus mainly on the first term, and then the first term here, and then the last term. So the leading term and then the constant. So the leading term was 2x cubed. So I'm just going to start from here, leading coefficient 2x cubed. We're going to take the coefficient 2, and we're going to find its factors, which are 1 and 2, because 2 is a prime number. Our constant was positive 5. 5's also a prime number, so its factors are 1 and 5. Then we're going to set up that p over q, that fraction we were talking about. So we'll take one of the numbers from here. We'll take 1, make it the numerator, and take one of the numbers from here. And if we actually distribute this, we do 1 over 1 plus or minus 1, 1 over 2 plus or minus 2, 5 over 1 plus or minus 5, and 5 over 2 plus or minus 5 over 2. This is going to give us all the possible solutions, but that doesn't mean all of these are the correct solutions. This is what is possible, and what we're going to do is we're going to pick each of these numbers, and we're going to use synthetic division to see if these will actually go into the original polynomial we had. If they do, we'll understand that it is a factor, and then we'll factor and we'll find a quadratic. We'll simplify into a quadratic because we're dividing, and then we will find out what the quadratic can factor or break into. So first we can pick 1. I always suggest going with 1, and so did my teacher. If 1 is one of the possible roots, always start with 1 because it's the easiest to work with. So we'll start with positive 1, and we'll do synthetic division. We're pretty much writing the original polynomial we were given. So it was 2x cubed minus x squared plus 2x plus 5. We're going to just write the coefficients. Hopefully by now you know enough about synthetic division. We're just going to solve, drop the 2, multiply that times 1, write the 2 under the negative 1. Negative 1 plus 2 is 1. 1 times 1 is 1. 2 plus 1 is 3. 3 times 1 is 3. 5 plus 3 is 8. I know I went through that fast, but hopefully again you have practice. Since we have an 8 at the end, we don't end with a 0. That means there's a remainder. So this 1 is actually not a factor. Since it's not a factor, we're going to eliminate that. That is not a possible root. So positive 1 does not work. Now let's move on to negative 1. And if negative 1 fails, we're going to move on to positive 1/2. Or you can move on to positive 5 because that's a whole number that'd be easier to work with. But you get the gist of it. You're going to just keep canceling out. It's almost like, I hate to say guess and check, but that's how the rational root theorem works. You're just going to check each possible answer to see to find the right one. So we'll move on to negative 1. We'll write our polynomial. Now we'll drop the 2. 2 times 2 times negative 1 is negative 2. Negative 1 plus negative 2 is negative 3. Times negative 1 is 3. 2 plus 3 is 5. 5 times negative 1 is negative 5. 5 plus negative 5, that cancels out and gives us 0. So luckily, negative 1 is a factor because we have no remainder. Knowing that it's a factor, we'll actually take whatever our answer is here, we'll rewrite it in terms of a polynomial. This was a cubic, what we started with, so we're going to reduce the degree by 1, and we'll get our leading term to be a quadratic. So if we write this in terms of a quadratic, we get 2x squared minus 3x plus 5, using these as the coefficients. Next, we're going to try to factor this. However, we can't factor this if you look at it because you can't use it using the guess and you can't do it using the guess and check method because this doesn't break apart perfectly. So what we'll do is we'll actually use the quadratic equation because completing the square is also kind of tedious. Remember, the quadratic equation is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Make sure you just memorize that. So that's what we're going to do here. Negative b is actually positive 3 plus or minus square root of b squared. Negative 3 squared is 9 minus 4 times a, which is 4 times 2, which is 8, times c, which is 5, so 8 times 5 is 40, minus 40 over 2 times 2, which is 4. We're going to simplify what's in the square root sign. We'll get 3 plus or minus the square root of 9 minus 40, which is negative 31 over 4. And we can actually factor out a negative 1, which the square root of negative 1 is I. So we end up getting 3 plus or minus I root 31 over 4. So our answers are negative 1, 3 plus or minus I root 31 over 4. You don't have to check the rest of these. Remember, the reason we couldn't get the 3 plus I, etc., as a possible rational root at the beginning is because this is an irrational root. This is the rational root theorem. This is an irrational root. So we're actually using the rational root we found, which is negative 1, to find the irrational root because the question asks us to find all possible roots. We got to find both the rational and irrational roots. So make sure to pay attention to that. Here's problem number 1a, very similar. What are all the possible rational roots of 3x cubed plus 7x squared plus 6x minus 8 equals 0? Then we're going to find all the actual roots that belong to this polynomial. Keep in mind that it's a cubic, so again, it's going to be hard to factor because it's not a quadratic. So we're going to try to simplify this into a quadratic using the rational root theorem and then find the irrational root as well. So our constant at the end of that polynomial was 8, and our leading coefficient was 3x cubed. So we're going to take those coefficients 8 and 3 and write out their factors. 8's factors are 1, 2, 4, and 8. 3's factors are 1 and 3. We're going to take each of the factors of 8, make it a numerator, and then make each of these 1 and 3 denominators and set up all the possible fractions. And actually, I forgot to mention that these are also ones I didn't include by accident when I was writing this out for you. So 1 over 1 is positive or negative 1. 1 over 3 is positive or negative 1/3. 2 over 1 is positive or negative 2. 2 over 3 is, you can see up here, positive or negative 2/3. 4 over 1 is positive or negative 4. 4 over 3 is positive or negative 4/3. 8 over 1 is positive or negative 8. And 8 over 3 is positive or negative 8/3. I forgot to include the positive or negative. Make sure you don't do that. That's very important. So since you can see here that 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible roots. This is a lot for us to check. Because of that, we can actually just do this on a calculator to find the first rational root. And what we'll do is we'll put the polynomial that you saw on the previous slide in for y1, and then we'll put in y equals 0 in the second y slot. Then we'll graph these and find where they intersect, and we'll see that the rational root is going to be 2/3 0 on a calculator. So 2/3, which is actually one of our possible ones, is the correct answer for the rational root. We'll take this rational root and do synthetic division so we can simplify to a quadratic, find the irrational root. So 2/3, so we'll set up the polynomial we were given on the last slide in the synthetic division format, 3, 7, 6, negative 8, just the coefficients, and then we'll actually divide 2/3 into it. So we'll drop the 3, 3 times 2/3 is 2, 7 plus 2 is 9, 9 times 2/3 is 6, 6 plus 6 is 12, 12 times 2/3 is 8, negative 8, plus 8 cancels out, gives us 0. So we're confirming that this is a factor. That's not the reason we did this. We did this to find the coefficients so that we could set up a quadratic. So we'll get 3x squared plus 9x plus 12. Using these numbers down here, we can pull out, we're trying to factor this now, so we can pull out a 3 because each of these coefficients is a 3 is a factor of, So you can pull out a 3 and you can simplify that, get x squared plus 9 divided by 3 is 3x plus 12 divided by 3 is 4. Now we can take this x squared plus 3x plus 4 and put it into the quadratic equation because this does not factor using the guess and check method. So we end up using that negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b is just negative 3, plus or minus the square root of b squared. 3 squared is 9, minus 4 times a, which is 1, so that's 4 times 1, which is 4, times c, which is 4, so 4 times 4 is 16, so we get 9 minus 16 over 2 times a, which is 1, so 2 times 1 is 2. Then we're going to simplify what's underneath the radical sign. 9 minus 16 is going to give us negative 7, so we get negative 3, plus or minus the square root of negative 7 over 2. If we factor out that negative 1, the square root of negative 1 is I, so we end up getting negative 3, plus or minus I root 7 over 2, and then you'll see our two answers up here. So that's how you solve that. Now let's move on to the last problem, problem number 2. We're going to find all rational roots of 15x cubed minus 32x squared plus 3x plus 2 equals 0. So in this case, what you're going to see is that when we begin the rational root theorem, first we're going to look at the constant, obviously, which is 2. 2's factors are 1 and 2 because it's a prime number. Then we're going to look at the leading coefficient, which is 15. The factors of 15 are 1 and 15 and 3 and 5. If we put these together, we end up getting and make the factors of 2 the numerators and the factors of 15 the denominators. Oops. You'll see that we get 1 over plus or minus 1 over 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1/15, plus or minus 2, plus or minus 2/3, plus or minus 2/5, and plus or minus 2 over 15. You can see that these are so many roots to test. These are actually 8 possible roots to test, just like the last problem. So what we can do is we can just use our calculator. We can plug this polynomial up here into y1 and then make y2 equal to 0, graph them, and then find the intercepts, and you'll actually see that all of the intercepts are rational. On the calculator, you'll see that if you expand your window enough, that the graph of this polynomial will pass through the x-axis 3 times. And if you actually find these intercepts by navigating around and finding where the polynomial actually intercepts the line y equals 0 or the x-axis, you'll see that x is equal to negative 1/5, 1/3, and 2. So I suggest that you try this on your calculator, but you'll see that there are no irrational roots. All of the roots are rational, and there are 3 of them. All the rational ones, we were able to find all of them on the calculator. So make sure you check that out using your calculator. It's pretty straightforward. And that's all I have for you today. I hope you enjoyed the video. If you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials to help us out. Also, check out our website and Gmail while you're at it. Thank you for joining me, and I'll see you in the next video on the conjugate root theorem. Thank you.